Okay, sir. Thank you, sir. Good evening, students.
Good evening,
Good
sir.
evening. Yes, yes. Others, can you hear me? Others, can you hear me? Yeah? Hello? Hello? Ritika, Ajay, can you hear me?
Yes, sir.
Yeah, Ritika, can you hear me?
Yes, sir.
Yeah, please. Okay, we'll continue with the topic. And today, possibly, we'll finish up with this chapter solids. We have to learn a lot of MCQs. Before that, the last part of the theory, we will finish up properties of solids. Yesterday, we learned with defects, different types of defects, stoichiometric defect and non-stoichiometric defect. In that, metal excess defect, metal deficiency defect. And we learned an important question, that is Farben. Farben stands for, F center stands for Farben, and this is what we learned, F center, and this is also called as color center. This is because of the electrons occupying the holes. We learned all that the holes is occupied by electrons are called as F centers. All that we learned yesterday. Color of a metal is because of F centers. You should know that. See here, this is an example. Here it should be an ion, but in place of an ion, electron is occupied. So this is called as F center. All right. So color is because of the F centers. All that we learned yesterday. We will continue with the topic today. Now, properties of solid. Some of the properties of solid which are useful in electronic and magnetic devices such as transistors, computers, and telephone, etc., are summarized below. Now, when we say properties, we are trying to talk about the electrical properties, majorly electrical properties, as well as the magnetic properties of the solids. So we will not be in detail talking about the transistors, how the solids are used, or computers. We will not talking about this. We'll be talking about electronic properties and the magnetic properties. So the first property what we're going to learn is electrical property. Solids are classified into following classes depending on the extent of conducting nature. Now we know that in the periodic table we have solids, we have liquids, and we have gases. In case of solids, we have metals and non-metals. Metals and non-metals. We know that all metals are conductors, and all metals are conductors, and all non-metals are insulators. Likewise, now a solid itself, the definition solid, the classification of solid itself can be classified into two as conductor and insulator. Now, metals, the electrical conductance of metal will not be same for all the metals. It will be different with metals. So that we are going to talk about here. And also, now a solid, we will have one more terminology that's called as metalloid. Metalloid is a solid which has metallic character as well as non-metallic character. When a solid having metal character as well as a non-metal character, they are called as metalloids. These metalloids can be also called as semiconductors. It is also called as semiconductors. We will learn about all that. Now, the first property, what we're trying to talk about is electrical property. Solids are classified into following classes depending on the extent of conducting nature. Solids which are conductors. Solids which allow the electric current to pass through them are called as conductors. All the metals are conductors because metals will allow the electric current to pass through. In case of metals, you should remember the charge carriers is electron. What carries current is electron. What are the charge carriers otherwise is electrons. So in any metal, the current is carried through the movement of electrons. Therefore, the charge carrier is called as an electron. These conductors are of further two types. One is a metallic conductor, the other one is electrolytic conductor. Now, the chapter is solids. This electrolytic conductor we talk about in solution state, conductor in aqueous medium or in solution state will be called as electrolytic conductors. So electrolytic conductors, we will talk about it a little later. Now conductors are two types. One is metallic and electrolytic conductor. Now the electrical conductivity of these solids is high in the range 10 to the power 4 to 10 to the power 6 ohm inverse centimeter inverse, Siemens per centimeter. Otherwise, per ohm is also called as Siemens. Siemens per centimeter is the unit for conductance. So you should remember the unit for conductance. Conductance. It is per ohm per centimeter, or it is read as Siemens per centimeter. SEIMEN. Siemens per centimeter. This is the unit for conductance. Now, electrical conductivity of these solids is high to the range 10 to the power 4 to 10 to the power 6, very high conductance, ohm inverse, centimeter inverse. Their conductance decreases with increase in temperature. So you should remember this. This is the first point. Conductivity is high for the solids. First point. There's a second point, the unit for conductance. The third and the important point is conductance decreases with increase in temperature. Now, why conductance increases with decrease in temperature? Because as we increase the temperature, there will be the resistance for the movement of electrons. Therefore, conductance will decrease. So these 3 points you are supposed to remember with respect to conductors. Electrical conductors. Solids are high conducting materials. The unit for conductance is per ohm per inverse, or Siemens and ohm inverse, centimeter inverse, or Siemens per centimeter, or Siemens centimeter inverse. We can call it like that also. The third point is conductance will decrease with increase in temperature, because on increase in temperature, the vibrations of electrons will increase. To and fro movement of electrons will increase, but not the flow of electron. Therefore, conductance will decrease on increasing the temperature. Next is insulator. Now, solids which do not conduct electricity is called as an insulator. Or solids which do not allow the flow of current to pass through them is called as an insulator. So, example for insulator: rubber, wood, plastic. These are a common example for insulators. So any solid which will not permit the current to pass through them or flow through them is called as an insulator. Example is rubber, wood, plastic, etc. The electrical conductivity of these solids are very low, 10 to the power minus 12 to 10 to the power minus 22 ohm inverse centimeter inverse. Excuse me. See the value here, 10 to the power minus 12 to 10 to the power minus 22, very, very low conductance. Therefore, they are the materials like rubber, wood, and plastic are called as insulators. The next one, what we have is semiconductors. Solids whose electrical conductivity lies between conductor and insulator are called as semiconductors. I hope that you are getting the definition for semiconductors, students.
Yes, sir.
Yes, sir.
Yes. Now, materials whose conductivity lies between a conductor and an insulator are called as semiconductors. The conductivity of these solids is due to the presence of impurities. Example, silicon, germanium, their conductance increase with increase in temperature. The electrical conductivity of these solids is increased by adding impurity. This is called as doping. Yesterday, I was talking about silicon. I told you silicon is belonging to carbon family. The valency of silicon is 4. The valency of silicon is 4. That means each silicon atom is bonded to 4 other silicon atoms like this. Now what happens if the temperature increases? The bonds break. When the bonds break, electrons are formed. When bonds break, what are formed? Electrons are formed. These electrons will start moving. Since this electron starts moving, what happens is it carries current. Therefore, we call silicon to be a semiconductor. In pure state, at a very low temperature, conductivity is minimum. But when we increase the temperature, what happens? The bonds break and starts moving. This is called as intrinsic semiconductor. So when the conductance of silicon is increased on increasing the temperature, then it is called as an intrinsic semiconductor. But there's a statement we read here: the conductance increases with increase in temperature. I told you this. The electrical conductivity of these solids is increased by adding impurity. So when an impurity is added, then we call that as a doping. Then we call it as what? Doping. Doping means addition of impurity is called as doping. Now, for an example, I have a silicon here. This is the availability of space. I'm trying to write it smaller. I hope that you're able to see what I'm writing. Now, I'm little, writing it smaller. Now, silicon valency is 4. Each silicon has 4 bonds. Now, what happened is, now this silicon atom is replaced by a trivalent element like boron. See this trivalent element like boron. Now, boron is an impurity here. See, when boron is introduced, boron has 3 electrons in the outermost orbit. 3 valency is satisfied. You can see here, there is a hole created, and here this electron here. Silicon has 4 bonds, therefore 1 electron will be here in silicon. But next to boron, there is a positive hole created. So this electron can move towards this hole. When this electron moves towards this hole, this electron gets filled this hole, and here there will be a hole created. So likewise, this movement of electron will take place. This is called as positive type semiconductor. Positive type, or it is called as p-type semiconductor. Why it is p-type semiconductor? Because the dopant, the impurity boron, is an electron deficient group. So that is why a hole is created. So whenever an impurity like boron or arsenic or a trivalent metal is doped, then the type of semiconductor what we obtain is called as p-type semiconductor. Followed with this? What is p-type semiconductor, positive type semiconductor? Likewise, if I have silicon here and silicon, I'll write silicon here also. All these are silicon atoms. Now, if one of the silicon atom is replaced by a pentavalent impurity. Now, when I say pentavalent impurity, like phosphorus, 5 electrons it will have in the outermost orbit. So 4 bonds are formed. The 5th electron will be free. This 5th electron will start moving. So this movement of the 5th electron will make this silicon also a conductor. Conductivity will increase. Now, since we are doping the pentavalent impurity, pentavalent means impurity whose valency is 5. 5 electron in the outermost orbit. 4 involved in the bonding, the 5th electron is free. Since this 5th electron is free, this will be called as N-type semiconductor, or it will be called as negative type semiconductor. Negative type semiconductor. So semiconductor is of 2 types. One is N-type and the other one is P-type. You can see when silicon is doped with phosphorus or arsenic, the 5th group element, we get N-type. I explained it here. This is because phosphorus has 5 valence electrons. I explained all this. Now, if a trivalent impurity is doped, if this gives rise to N-type semiconductor because current carried by electron. When silicon is doped with gallium, indium, or aluminum, or 3rd group element, or boron, we get P-type semiconductor. I explained it as what is P-type semiconductor here. Is it clear?
So can you do that N-type semiconductor again, sir?
N-type semiconductor, I will do it again. Maybe I'll do it here. I will do it here. Now, this is silicon. This is silicon. Now, the valency of silicon is 4, meaning each silicon is bonded to 4 other silicon atoms. Now, one of the silicon atom, now we're doping. Doping is adding impurity. One of the silicon here is removed or replaced by phosphorus. Phosphorus has 5 electrons in the outermost orbit. Each electron will involve with bonding with silicon. 4 covalent bonds will be formed. Sharing of electron is called as covalent bond. The 5th electron is left out free. This 5th electron, which is left out free, movement of electron will lead to the conduction of current or carry current. Now, since electron is in excess and electron is negatively charged, it's called as N-type semiconductor, or it is called as negative type semiconductor. Did you follow this now? Did you follow this now?
Yes,
Yeah.
sir.
Yeah. Now, superconductors, superconductivity. When any metal loses its resistance for electric current, it's called a superconductive conductor. Now, to be more precise and more in simple words, if any material has no resistance for the flow of electron, they will be called as superconductors. So if as the reciprocal of resistance. So if conductance is high, it means the resistance should be what? Low. Now for superconductor, resistance is almost zero. Resistance is almost zero. When resistance is almost zero, a material can be a superconductor. So Kamerlingh Owens in 1913 observed this phenomena at 4 Kelvin in mercury. Mercury is a liquid metal at 4 Kelvin. Just imagine 4 Kelvin. 4 Kelvin is around minus 269 degrees Celsius. Minus 269 degrees Celsius. Very, very low temperature. At 4 Kelvin of mercury, the resistance for current at very low temperature, around 2 to 5 Kelvin, are called as superconducting materials. So, what are superconducting materials? A material which offer no resistance, 100% flow of electricity at very low temperature, around 2 to 5 Kelvin, are called a superconducting material. The phenomenon is called as superconductivity. See this complex: niobium gallium alloy, germanium alloy. Niobium is a rare earth element, F block element, and lanthanides, lanthanum, barium, copper oxide. These combinations at low temperature, they will behave like superconductors. Remember, 1 or 2 examples of superconductors. The following are the important applications of superconductors. Moving trains, the wheels of the train. Okay, so building supermagnets, aviation, transportation, power transportation, these all are the applications of superconductivity. Is there any clarifications if till here?
No, sir.
Can we continue? I don't think so. Today also we can finish with the topic because a lot of numeric, a lot of MCQs we have to learn, not numericals. MCQs we have to learn. So I hope that you followed with the electrical properties of the solids. Now comes the magnetic properties of the solids. Very simple concept. Based on this, 100% there will be a question in your regular exam as well as in your competitive exam. This is the very important concept in your solids chapter. Now, magnetic properties of solids. Based on the behavior of a substance, when placed in the magnetic field, they are classified into 5 classes. Solids are classified into 5 classes. So if a material is placed in the magnetic field, it behaves different. North pole and south pole, if I keep, this material behaves in different ways. How many different ways? It behaves in 5 different ways. Therefore, they are classified into 5 classes. The first one is diamagnetic. The first one is diamagnetic. See, observe this carefully. This is the electronic configuration for diamagnetic. Now, these are our orbitals. Now, when I say these are our orbitals, do we have any unpaired electrons?
No, sir.
No, they all are paired electrons. When a material having paired electrons, when they are placed in the magnetic field, they will be feebly repelled. They will be moving away from the magnetic field. Those kind of materials are called as diamagnetic materials. So material which are repelled from the magnetic field, which move away from the magnetic field, are called as diamagnetic substances. Now, this diamagnetism is because there is no unpaired electron. All the electrons are paired in a system. See, feebly repelled by the magnetic field. Non-magnetic metallic elements like except oxygen, sulfur, inert gases, and species with paired electrons are diamagnetic. See, oxygen is diamagnetic, sulfur is diamagnetic, all inert gases, noble gases are diamagnetic, and any species with paired electrons are diamagnetic because they will be repelled against the magnetic field. So examples they've given: titanium dioxide, it's not clearly visible, titanium dioxide, vanadium pentoxide, sodium chloride, benzene, all these are examples for diamagnetic substances. They are used as an insulator. They're used as an insulator. Diamagnetic substances are used as an insulator. Now, why diamagnetism, they'll ask you. Why material exhibit diamagnetic property? You should tell that it is because of the absence of unpaired electrons, or it is because of the presence of paired electrons. Now, paramagnetic substances, the next one, attracted by the magnetic field due to the presence of permanent magnetic dipoles. Magnetic dipoles are nothing but unpaired electrons. You can see the configuration here. This has unpaired electrons. Since they have unpaired electrons, they will be attracted towards the magnetic field. And these tend to orient themselves parallel direction to the field and thus produce magnetism in the substances. So materials which are attracted towards the magnetic field, they are called as paramagnetic substances. That is because of the presence of at least one unpaired electron. Here they have shown two unpaired electron, but at least one unpaired electron. Example, this oxygen cannot be considered as, oxygen can be considered as paramagnetic also. Oxygen, CO2 plus, ferric ions, titanium oxide, titanium trioxide, vanadium oxide, vanadium dioxide, cuprous oxide, all these are examples for paramagnetic. We will learn this paramagnetic character in a chapter, D block elements, in detail. I will write the electronic configuration and explain the magnetic property, why magnetic property arises, all that we will be learning in a chapter called as D block elements later. These paramagnetic materials are used in electronic appliances. Now, if a material contains unpaired electron, minimum one unpaired electron, they will be attracted towards the magnetic field. Those kind of materials are called as paramagnetic species. And there are examples, there are so many examples mentioned here, and they are used as an electronic appliances. The third is ferromagnetic. Now just observe the electronic configuration. There are 5 unpaired electrons, and all the dipoles are in the same direction. All the unpaired electrons are oriented in the same direction. So permanent magnetism, even in the absence of magnetic field, above a temperature called as Curie temperature, there is no, this is magnetic field. Above a temperature called Curie temperature, there is no ferromagnetism. So what is ferromagnetism is, if a material contains more number of unpaired electrons. Now, paramagnetism we learned, if it contains minimum one unpaired electron, it's called as what? Paramagnetic. If this material contains more number of unpaired electrons, they will be strongly attracted towards the magnetic field because of the presence of more unpaired electrons. Those kind of materials are called as ferromagnetic, more number of unpaired electrons. So iron, nickel, cobalt, chromium. For an example, if you take iron, atomic number of iron is 26. The electronic configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Now, if I represent the d orbital for our understanding, now d subshell has 5 orbitals, 1, 2, 3, 4, 5, and 6. Now you can see there's 4 unpaired electrons. Since they have 4 unpaired electrons, this will be strongly attracted towards the magnetic field. Therefore, iron is an example for ferromagnetic species. So if a material contains more number of unpaired electrons, they will be strongly attracted towards the magnetic field, and they will be called as ferromagnetic. Clear with this? These magnetic properties are important. Next is antiferromagnetic. Now you observe here the configuration for antiferromagnetic. Now one is upward orientation, the other one is downward. Upward, downward, upward, and downward. Now the alignment of unpaired electrons are in the opposite direction. Equal number of unpaired electrons are in the opposite direction. Therefore, the magnetic moment will be zero, or the magnetic property will be zero. Those kind of materials are called as antiferromagnetic. Even though we have many number of unpaired electrons, the orientation of the electrons or the alignment of electrons are equally and opposite. Therefore, they will not show magnetic property. And those kind of materials are called as antiferromagnetic substances. Example, manganese oxide, manganese dioxide, manganese oxide, ferrous oxide. So many examples are there. Chromic oxide, cobalt oxide, cobalt tetraoxide, all that. So many examples. The next is ferrimagnetic. These arise when there is net dipole moment. What do you mean by dipole moment is represented by letter mu. Charge into distance is called as a dipole moment. Here, there is charge and there's also distance, but equal and opposite. Therefore, it becomes zero. Net dipole moment becomes zero here. But here, if you see, we have 3, 4, 5, 6 electrons. 1, 2, 3, and 4 are downward, and this 2 are upward. Orientation, alignment. Alignments are in different direction. So if I say this and this gets cancelled, this and this gets cancelled, but there will be a dipole moment because of these 2 electrons. There will be magnetic property because of these 2 electrons. Those kind of materials will be called as ferrimagnetism. Example for ferrimagnetism is magnetite. This is magnetite, Fe3O4. All ferrites, FeRrITs. These will exhibit magnetic properties. Now, I will take some time. I want you people to go through this magnetic property so that we'll continue with some of the questions now. Any clarification so far, you can ask me. So the chapter. Yes.
So could you explain that ferrimagnetic again, sir?
Now, ferrimagnetic is upward arrow, downward arrow, downwards. Now see, this is upward arrow, electron, clockwise rotation. This is anti-clockwise rotation. Assume that they cancel. Here also downward and upward it cancels. But what about these? These 2 are excess. So these 2 are in the same direction. Therefore, they will exhibit a permanent dipole moment. They will have charge and distance. Dipole moment will be there. So this will show magnetic property. Did you understand? Those are called as ferromagnetic. Even though we have, see, we'll have unequal number of what? Upward alignment and downward alignment. Clockwise rotation, anti-clockwise rotation. So in case of what? Antiferromagnetism, you can see here, it is equal clockwise and equal anti-clockwise. Clockwise, anti-clockwise, clockwise, anti-clockwise. Therefore, the net dipole moment is 0. Here, even though we have unpaired electrons, unequal number of what? Clockwise and anti-clockwise. Therefore, this will show permanent dipole moment, or they will show net dipole moment. This exhibit magnetic property. Followed?
Yes.
Followed? Go through this chart, table. We'll continue. I thought I'll finish with the questions today. Not going to happen. Is there any clarification? This is important. Electrical property, magnetic property, you should know. We have not done questions with respect to the imperfections of the solids also. I think on Friday we'll finish with this topic. Okay. Dielectric property. Dielectric substance is that which does not allow the electricity to pass through them. But on applying the electric field, induced charges are produced on its faces. In an insulator, the electrons are strongly held by individual atoms. When electric field is applied, polarization takes place. When electric field is applied, polarization takes place because nuclei are attracted to one side and electrons are cloud to the other side. As a result, dipoles are created. Such type of crystal shows the following property. Now, dielectric properties, generally we talk for material which does not allow the electron. To understand the term called as polarization. Now, what is this polarization? Now, we know that in an atom, we have a nucleus at the center and we have electrons revolving around the nucleus. Nucleus is at the center and we have electrons revolving around the nucleus, called as orbits. You know this very well. Now, nucleus contains protons. Nucleus is what charged? Nucleus is what charged?
So positively charged.
Electron is?
So negatively charged.
Yeah. Now, when I say polarization, now what happens? See, what is electron cloud? They are using a term called as electron cloud somewhere. I heard, yeah, this is electron cloud. What is electron cloud? That is a space or region outside the nucleus where you expect the electron to be present. That's called as an electron cloud. Space or region outside the nucleus where there is maximum chances of finding electrons is called as electron cloud. Now, electrons are negative and nucleus is positive. Now, if, see, this is spherical. Assume this is to be a sphere. Now, if it becomes like this, this is electron and this is nucleus. Nucleus is positive. See, this kind of, if the atom gets distorted means change in shape, distorted, then that process is called as polarization. That process is called as polarization. So when electric field is applied, polarization takes place. Nuclei are attracted towards one side and electron cloud to the other side. As a result, dipole is developed. Such type of crystals show the following property. One is piezoelectricity. Piezoelectricity you should know. In some of the crystals, the dipole may align themselves in an orderly way so as to give some net dipole moment. When mechanical stress is applied in such crystals so as to deform them. Excuse me, I'll drink water. Sorry. Now, some of the crystals, the dipole moment may align themselves in orderly way so as to give some net dipole moment. When mechanical stress is applied in such crystals so as to deform them, electricity is produced due to the displacement of ions. So this is polarization. Any crystal in the presence of electricity, the positive nuclei move towards one direction and electron move towards the other direction. That is called as polarization. Because of this polarization, they have different property. One is called as piezoelectric property. Some crystals, dipole moment may align themselves in an orderly way. This is a dipole moment. Why this is a dipole? One is positive, the other one is negative charge. When these dipoles are arranged in an orderly way to give some net dipole moment. So it is not one nucleus and one electron. In a solid, there will be many number of electrons and many number of nucleus. If all of them orient in an orderly way, the net dipole moment will be very high. During that time, when stress is applied on such crystal, they undergo deformation. The crystal will undergo change in shape. The solid will undergo change in shape. Then electricity is produced due to the displacement movement of ions. Thus, the electricity thus produced is called as piezoelectricity, and the crystals are called as piezoelectric crystals. Example, quartz, Rochelle salt, sodium potassium tartarate is called as Rochelle salt. You understood what is piezoelectric? Any solid when placed in the electric field, they undergo distortion, they undergo polarization. And when all the dipoles are orderly arranged, the net dipole moment will be developed. When net dipole moment will be developed, for those kind of crystals, when a mechanical stress is applied, the material undergo deformation. Electricity is produced due to the displacement of ions. Thus, the electricity thus produced is called as piezoelectricity. And the example is quartz and Rochelle solid. You should remember this. The next one is pyroelectricity. On heating some polar crystals, you should know what is polar crystals. We have learned it in the first class. The crystal which has polarity, like NaCl is a polar crystal, produce some electric current. The electricity thus produced is called as pyroelectricity. Pyroelectricity means a crystal, polar crystal on heating, they produce small electric current, and those are called as pyroelectricity. Next is ferroelectricity. In some of the piezoelectric crystals, a permanent alignment of dipole moment is always there, even in the absence of electric field. However, on applying field, the direction of polarization changes. This phenomena is called as ferroelectricity, and the crystals are ferroelectric crystals. Example, potassium hydrogen phosphate, barium titanate. So ferroelectricity is it's possible only in piezoelectric crystals. We learned what is piezoelectricity. Piezoelectric crystals, a permanent alignment of the dipole is always there, even in the absence of electric field. However, when a field is applied, the polarization changes, the direction changes. Now assume in piezoelectric material, the dipole moment is aligned like this, Now, when I say ferroelectricity, when electric field is applied, the direction will change. Those kind of material are called as ferroelectricity. The next is anti-ferroelectricity. In some crystals, the dipoles in alternative polyhedral point up and down so that the crystal does not possess any net dipole moment. Anti-ferroelectricity, they will not have any net dipole moment. They will not conduct electricity. Such crystals are said to be anti-ferroelectric. Example, lead zirconate. Lead zirconate. So just go through this material. The topic is done. We need to work out some MCQs. Possibly we'll work out in the next class. Any clarification? Piezoelectric material examples you should remember. Pyroelectric, likewise ferroelectric material. You should remember some of the examples. Is there any clarification? Sir, yeah.
Sir, could you do that ferroelectricity again, sir?
Okay. Now, what is piezoelectric material? See, piezoelectric materials are material which develop dipoles when, see here, some of the crystals, dipole may align themselves. This is a dipole. They will align themselves in an orderly way. So this is a dipole. When I say this is a dipole, maybe we'll represent, okay, maybe I will write it here a little larger. Now dipole, this is dipole. Dipole moment is represented by arrow and like this. Now for an example, if I take HCl, it's not a solid. It's a liquid state or gaseous state. Chlorine is electronegative. We write the electron moves towards chlorine and electron move away from nitrogen. Therefore, dipole moment is represented like this. What does this indicate? Electrons are moving towards chlorine. Electrons are moving away from hydrogen. Since electrons are moving away from hydrogen, it gains a positive charge. That's what is this. Now, all the dipoles are aligned like this. Assume. It's an orderly arrangement in piezoelectric material. Now, even in the absence of the electric field, the arrangement is like this in piezoelectric material. But when you apply the electric field, the direction changes like this. I'm writing it opposite. It can be in any direction. So these kind of materials are called as ferromagnetic materials, ferroelectricity otherwise. Followed with this now?
Yes, sir.
Yeah. All right. Any clarification? The theory part and other problems we have worked so many days. Any clarifications you can ask me if you have. But I yeah, tell me. Someone is talking to me.
Can you please explain p-type semiconductors, sir, once again?
P-type semiconductors once again. Now, silicon is a non-conductor insulator in pure state. The valency of silicon is 4. So I will just represent a part of silicon crystal like this. What do you mean by valency?
The number of outermost electrons in the
No,
metal.
combining capacity is called as valency. See, noble gas has 8 electrons in the outermost orbit, but noble gas valency is 0. Combining capacity is called as valency. Silicon has 4 electrons in the outermost orbit. It can combine with 4 more other silicons. That is why the silicon valency is 4. See, these are the electrons contributed by silicon. These are the electrons contributed by silicon. Now, when I say p-type semiconductor, if there is an impurity in place of this silicon, a trivalent element like boron is doped. Boron has 3 electrons in the outermost orbit. When I say boron has 3 electrons in the outermost orbit, what happens? 3 bonds are formed. 3 bonds are formed. You can see here. 4th bond is not possible. This silicon has 1 electron. Here there is a hole created. Now, these electrons, if this electron moves here, there will be a hole created here. Like that, movement of electrons and holes will be happening in the crystal. Due to that, they will start conducting electricity. Now, here, because this is electron deficient, we call it as p-type semiconductor, positive type semiconductor. Did you understand?
Yes, sir. Thank you, sir.
Yeah. Any other clarifications quickly? I think in the next class only we will solve questions. This class we will not be in a position to solve questions. Already it's time. So we will be solving questions based on solids only in the next class. That's on Friday. Yeah, any clarification you can tell me. Otherwise, I will stop the class for now today. You can ask me from any of the topic in the sense this chapter, any of the topic what we have learned, you can ask any of the topic, not only from today's class.
No doubts from my side, sir.
Okay, anybody else? So I don't know how many people worked out the problems. Did you bother to see the videos again, and are you noting down the problems, what I'm teaching, MCQs, all that? Is there any clarification? You should ask me. Any clarifications if you have? All right. No clarifications? Students,
No,
otherwise, yeah.
Yes, sir.
Yeah, okay. We'll start with the MCQs, maybe possibly in the next class. Mahendran sir, can I log out, sir? For now? Hello? Madam, can I log out, ma'am?
Hello, sir.
Yeah, Mahendran sir, can I stop the class, sir? I'll continue in the next week, next class.
Yes. Yeah. Thank you.